Hi, this is Dr. Sweeney, and what we're going to be talking about today is about parametrization. And parametrization is an incredibly powerful and very handy set of tools that we use whenever we're really doing work with physics or any kind of applied mathematics. What it does is it allows us to imagine things, and we'll use the basic example of moving in space, but not moving in space at some kind of like constant rate where x and y are related in some kind of random way, but along the lines of with regard to another variable, and oftentimes that other variable is, we're going to call it t. So like for example, we might have a particle moving in two-dimensional space where what we can say is that where it's moving horizontally is going to be dependent upon time, and where it moves vertically is also going to be dependent upon time. And so we'll have x and y are two variables actually written as functions of this third parameter t. Okay, and so then what we get is we get a different kind of like explanation for this particular function, right? We say that the function's been parametrized, all right? And what it does is it opens up all sorts of new possibilities for us, particularly, like I said, with regard to applications in physics. So let's begin with a demonstration of parametrization. Suppose that what I have is I have a circle of radius 4. Okay, so it's got our circle of radius 4, and I want to imagine that I have a particle. My particle is moving around this circle. Okay, now what I know is that the equation of that circle is going to be y equals, not y equals, but x squared plus y squared equals 16. Okay, that's basically your equation of the circle if we assume that we're going to start at 0, 0. Okay, with the radius of 4. Now, another way that I could actually write this is I could actually write this as, I could imagine that I'm moving around the circle, and what I'm going to have is instead of the values being dependent upon x or being dependent upon y, I can imagine my values being dependent upon t, where t is this angle right there, okay, in radians. And so in that case, what I get is that x will end up equaling 4 cosine t, and y will end up equaling 4 sine t, right? Where t is an angle in radians. The value t here is called a parameter. What we've done is we've added another piece here, okay, or another variable. So t is called the parameter, and what you'll notice is that what we'll get is we'll continue to get the same exact x and y depending upon our values of t, right? Okay, so what we can do with this is we can imagine that we've got a table, and our table will have t, and we'll have x of t, okay, which is just our x, and we'll have y of t, which is our y. So when t is 0, x ends up equaling 4, and y ends up equaling 0. Okay, and that's where we're at. This one right here ends up being 4, 0, right? Okay, you know, if you're thinking about it, a unit circle or a circle with the radius of 4, not rather a unit circle, but a circle with radius of 4, there you are. Let's say now we use t is pi over 4, okay? So now what we get is we get 4 times root 2 over 2, which is going to end up being 2 root 2. And for our y over t, we're going to get 2 root 2 as well, right? Okay, and so if we imagine at a 45-degree angle right here, okay, we're at the point 2 root 2, comma 2 root 2, okay? And our value for t now, right, our t2 is going to equal 45 degrees. So in the most basic way, that's actually how our parametrization works. What we do is we add in another variable, like in this case adding in t, which represents an angle that will relate x and y. Okay, so x and y are still related, okay? It's just that we've now added this extra variable t, which actually gives us even more information about this particular figure. So what that leads us to is it leads us to a definition of some very important ideas. The first, let's say that we have x and y are continuous functions of t. Okay, so now what we've done is we've rewritten our functions x and y, or our big function f of x, for example, as a function of t. And we have x equals x of t and y equals y of t. Okay? They're called the parametric equations. So they're called the parametric equations. And t is called the parameter. The set of points, xy, obtained as t varies over the interval I is called the graph of the parametric equations. And the graph of the parametric equations is called the parametric curve. Okay? And it's sometimes denoted, or plane curve, and it is denoted by C. Now, the thing is that if we look at these things statically, we don't really see any difference between what we have in terms of a parametric equation and what we get when we actually look at just a normal rectangular equation. What we're going to see is that it actually gives us an added piece of information. So let's take a look at an example. So let's say, for example, that what we have is x of t is going to equal t minus 1, and y of t equals 2t plus 4, and we're only concerned with our values of t along the interval -3 less than or equal to t less than or equal to 2. So this is I, and you'll notice that both x of t and y of t, they're both continuous everywhere on the real line. And let's say, for example, that what we want to do is we want to graph the parametric equation. I'm going to graph the parametric curve. So what I'm going to do is I'm going to first set up, I'm going to have t, okay? And then I'm going to have x of t, and then I'm going to have y of t, okay? Or I'm actually going to have a value of x, and I'm going to have a value of y. Now, these x of t's and y of t's, they're actually the functions that are going to give us x and y, so maybe we ought to just rewrite these as just x and y. But what's really important is that x of t and y of t are actual functions that didn't generate for us rectangular coordinates. So let's see. Let's say I have -3, -2, -1, 0, 1, and 2. So those are all the integer values along that interval. So we'll start with x of t, and x of t is t minus 1. So x is going to be -4 when t is -3. It'll be -3, right? Because we're just going to subtract 1 from every t. Then -2, then -1, 0, and 1. As for y, a little bit trickier, but y of t is going to end up being, let's say, 2 times -3 plus 4. Okay, so that's -2. And then we'll have 2 times -2 plus 4, and that's equal to 0. Then we'll have 2 times -1 plus 4, that's equal to 2. And you can kind of see that it'll continue to go on because it's linear. 0, 2, 4, 6, and then 8. Okay? And so those are the values for y. Now what I'm going to do is I'm actually going to graph them in order, right, as t increases. Now t is not going to show up on this graph. All that's going to show up is my x and y values. But t is going to be implicit in there. It's the parameter. Okay? And oftentimes that's actually where we're going to use things like implicit differentiation. Is we've got this missing t, the t that doesn't show up. So we'll start out and we'll say, okay, when t is -3, I'm going to be at -4, -2. So 1, 2, 3, 4, -2. So we're right there. Okay? There's -4, -2. Then my graph, I'm going to go to -2, -3. So -2 and then -3. Or excuse me, when t is -2, I'm going to be at -3, 0. So there we are, -3, 0. Okay? When t is -1, I'm going to have -2, 2. -2, 2. Okay? Then I'll be at, when t is 0, we're at -1, 4. So -1, 4. And then I have 0, 6. Or, 0, 6. Okay? And finally, I'm going to be at 2, 8. And so what you can see is I've got this graph right here. Okay? If my original graph was a little bit better, you'd see that it's just a straight line. Okay? That it's completely linear. And that the slope of the line ends up being equal to 2. All right? We'll look at why that's the case in just a moment. But that's basically how you're going to go about graphing these parametric equations. Right? You'll plug in values of 2. Okay? And you'll get x's and y's for each one of the 2's. Now, one of the things that I should actually do, okay, is I'm actually not going to include those lines that go outward because I'm only interested in the parametrization from t to negative 3 to 2. So it's only this particular section of the graph inside of the Cartesian plane. Okay, so it's only going to be this top and this bottom part. Okay, it's actually not going to extend out into infinity like we would normally think of a curve. Okay. What about this parametrization? We'll take another example. Let's say x of t equals t squared minus 3. Y of t is going to be 2t plus 1. And we're going to be looking at t less than or equal to negative 2, less than or equal to 3. Now, if I take a look, I'm looking at my functions. 1, here's my interval I. And on this interval, t squared minus 3 and 2t plus 1 are continuous. They're actually continuous everywhere, but we do want to make sure that we check that. And now, what I'm going to do is I'm going to set up my t. I'll have my x and my y. All right, and I'll construct a table for this. Okay, so when t is negative 2, we'll do negative 2, negative 1, 0, 1, 2, and 3. When t equals negative 2, we end up with x is going to equal 4 minus 3, so that's 1. Then 1 minus 3, that's negative 2. 0 minus 3 is negative 3. 1 will be negative 2 again. 2 will be 1. And 3 will end up equaling 6. So you can kind of see the parabola and the x values. That doesn't actually mean that our function is going to necessarily be a parabola. It could be something different. So we're going to see. Now let's take a look at y of t. We'll plug in negative 2. And so that's 2 times negative 2 plus 1, which is going to end up equaling negative 3. Then we'll have 2 times negative 1 plus 1. Okay, and that's negative 1. And then we'll go up by 2 because this is linear. So this is going to be 1, 3, 5, and 7. And so now what we have is we have a table of values that we can actually use to graph. And the cool thing about this is it won't be perfect sometimes. Sometimes it will be, like with linear equations. It could probably be very good. But what it will be is it will be pretty good. And it'll give you a general idea of what this parametric curve looks like. Okay, so now we're going to go, we've got 1, negative 3. So I'm just going to use my x's and y's. So we're going to go 1, negative 3. Okay. Negative 2, negative 1. So negative 2, negative 1. So there we go. So what I'm going to do is I'm actually going to connect these because this is the path. So now in the last case, the path was pretty straightforward. I don't know if that's necessarily the case here. Okay, so I've got negative 2, negative 1. Then I'll have negative 3, positive 1. Okay, there you kind of see. Okay, so there's that next step. Negative 3, positive 1. Then negative 2, positive 3. Okay, 1, 5. 1, 1, 2, 3, 4, 5. 1, 5. And then 6, 7. So there's 6, 7. And what you can see is that this parametric curve is a portion of a sideways facing parabola. Okay? And once again, notice that I only graph the curve for the values of t from negative 2 up to 3. All right? And in fact, what we'll see, or what you'll see as you do more work in physics, is that this also gives me a direction. Because what I'm doing as t increases, okay, is I'm moving in this direction along the curve. All right, so it gives me that extra added piece of information. Now, let's suppose that what we want to do now is we want to actually eliminate that parameter. We just want to write our function in terms of just x and y. And sometimes this can be kind of handy. And we're going to see later on how it is that we might be able to actually add a parameter or parametrize a function. But let's first take a look at eliminating the parameter. So let's say, for example, we start out with x, the one that we just saw. And we already kind of know what this looks like. It's going to be a sideways parabola. But let's take a look and see how it is that we might, in fact, generate our function. So what we're going to need to do is we need to write either x or y, we need to write t as a function of x or y. And then what we'll do from there is then we will substitute and simplify. So we'll start out with this. This is the most simple way to go about doing this. So, for example, I might say to myself, well, I want to make x equal to t squared minus 3. And then I'm going to, figure out what x is and then plug it in for t. But I think actually probably what would be best is let's go out and let's actually find what y is, because y is linear. So let's say y equals 2t plus 1. Okay, so y minus 1 equals 2t. And so t is going to equal just y minus 1 over 2. Okay? Then what we'll do is we'll substitute. So we'll substitute this, and we're going to get x equals, and this is going to be y minus 1 over 2 squared minus 3. So we substitute t in, substitute this function in for t. And then we simplify. So this is going to end up being x equals y minus 1 squared over 4 minus 3. And when we multiply by 4, what we can end up with, or we could just rewrite this as x equals 1/4 y minus 1 squared minus 3. Okay? And what you'll notice is the sideways facing parabola with its vertex at 3, -1, or should be -3, positive 1, right? This one right here, -3, positive 1. All right, and it's got a p of equal to 1, right? Okay, because 1 over 4p. So basically, it's going to be a pretty standard looking parabola, or sideways facing parabola. Excuse me. So all we needed to do in order to eliminate that parameter is we needed to actually substitute in. We needed to figure out what t was in terms of y or in terms of x, and then substitute it into the other equation. Now there's one last piece here, and that last piece is this interval here from -2 to 3. So what we're going to have to do is we're going to have to define the interval in the xy plane. And how we're going to do that is we're going to go in and we're going to figure out what the xy values are when t equals -2 and t equals 3. So I can actually go back up to my table here, and when t is -2, x is 1, -3. Okay? So we're going to be, the interval here is going to be from 1, -3, and then to 3, that's going to be 6, 7. So it's going to go from 1, -3 to 6, 7. So we only want this function on that interval I. Let's take a look at another problem. Let's say, for example, I have x of t equals 2t plus 4, and I have y of t equals 2t plus 1. Now, you might think to yourself, well, y is linear. That's probably the easiest one to do. But in this case, we probably want to think a little bit more and consider that probably we want to start with x here in this case because of that square root. So x is going to equal the square root of 2t plus 4, and then I'm just going to square. So x squared is going to equal 2t plus 4. All right. By the way, I should add in that we're going to go from -2 to less than or equal to t, less than or equal to 6. Okay. So x squared will be 2t plus 4. Then we'll get x squared minus 4 equals 2t. And so t is going to equal x squared minus 4 over 2. Substituting in now into y, we'll get y equals 2 times x squared minus 4 over 2 plus 1. And this then equals x squared minus 4 plus 1, which equals x squared minus 3. So we'll construct our table, and we'll get t and x and y. And so when t is -2, we get x of t is going to be the square root of 2 times -2 plus 4, which equals 0. And y will be 2 times -2 plus 1, which equals -3. when t is 6, that's the other end, right? Because that's the top end of our interval. We're going to get the square root of 2 times 6 plus 4, which equals 4. That's square root of 16. And then we'll get 2 times 6 plus 1, and that's 13. So our rectangular equation is going to be y equals x squared minus 3 from 0, negative 3 to 4, positive 13. And that is the parametric curve that we have drawn here. Let's take a look at another class of functions now that are a bit different, right? Okay, now we've got x of t equals 4 cosine t and y of t equals 4 sine t. And we saw this earlier on. This was the first one that we looked at. And what you'll notice is that if we were to actually solve for t, what we'd get is we'd get some kind of inverse trig function. And that might not be the most efficient way to go about doing things, okay? So instead, what we're going to do is we're going to go in here and we're actually going to utilize one of the Pythagorean identities. We're going to utilize the fact that cosine squared t plus sine squared t, okay, equals 1. It's a really handy little fact, okay? So cosine squared t plus sine squared t equals 1. And so what we're going to do now is we're going to say, okay, well, let's let x equal 4 cosine t, okay, and y is going to equal 4 sine t. And then we'll, instead of figuring out what x and y are in terms of t, we're going to find them in terms of sine t and cosine t, all right? And then utilize some, use that trig function. So this is going to be giving me x over 4 equals cosine t, and I'll get y over 4 equals sine t, okay? So if I put these together, right, remember that cosine squared t plus sine squared t equals 1. So what that means is that x over 4 squared plus y over 4 squared equals 1. So what I'm left with is I'm left with x squared over 16 plus y squared over 16 equals 1. Multiplying both sides by 16, I end up with x squared plus y squared equals 16. And there we go. Now, you'll notice that in this case, because we have the trig functions, that utilizing these trig identities actually makes the parametrization or eliminating the parameter a lot easier. Here's the other thing about them. Because they're periodic, we're going to have to really seriously consider what this curve looks like. So let's take, for example, we look at the interval, right? We want t and our x and our y. So when t is 0, x, right, is going to equal 4 times 1, which equals 4. And y is just going to end up equaling 0 because 4 times sine 0 is 0. When t is 2 pi, we're again going to get 4 times 1, and so that's going to be 4, and we're also going to end up getting 0. So this curve, x squared plus y squared equals 16, is going to go from 4, 0 to 4, 0. Now, but what we want to think about, now remember this is a trig function, so what you want to think about is, well, what's the path in between? Well, if I were to kind of imagine what the graph is going to look like, yeah, I'm going to start here at 4, 0, but I need to go everywhere in between, right? Okay, so here's 0, 4, here's negative 4, 0, and here's 0, negative 4. So everywhere in between 0 and 2 pi for t is everywhere along the lines of, and that's a terrible circle, but you can get the idea, that basically we're going to get the entirety of that circle, right? So the parametrization is actually not one part of the circle, it's the whole circle. It's not just this point at 4, 0, it's in fact the entirety of the circle, okay? And that's because we're considering everything within the interval, right? We're going to go from 0 to 2 pi. Now, kind of handy thing to think about here is the fact that the parametrization made that very obvious. Since we're going from 0 to 2 pi, you think, okay, well, it's a circle. I'm going to move from 0 to 2 pi on that circle, okay? It gets kind of lost inside of the rectangular equation. And so hence one of the values of the parametrization is to actually show us that there's going to be a full path that we're traveling. So a second skill that we're going to want to actually get good at too is to find a parametric equation to represent the particular graph. So for example, y equals x squared plus 2x. How do we actually write this in terms of a parameter t? Now the simplest way, right, like the base case, is what we do is we say, okay, well, we're going to let x of t just simply equal t. So let it equal the identity function. So then y is just going to equal t squared plus 2t. Done. Okay, there's the parametrization. On the other hand, what if we had, like, let's figure out a second one. We want a different set. And so let's figure what would happen if we chose a different x of t. So let's say, for example, we let x of t equal t minus 2. Okay, so we're going to take it and have it be t minus 2. Then y of t is going to end up being t minus 2 squared plus 2 times t minus 2. This gives me t squared minus 4t plus 4 plus 2t minus 4. Okay, which ends up equaling t squared minus 2t. And so that's our other parametrization. It's going to go from x of t equals t minus 2 and y of t equals t squared minus 2, or t minus 2 times t, which kind of makes sense given that that's basically this except with a different parametrization for x. Okay? Now what happens if what we want to do is we actually want to put it on a bounds? So let's say for our interval is going to go from 0, 0 to 1, 3. Okay? For the first parametrization, right, x of t equals t, okay, and y of t equals t squared plus 2t, what we'll do is we're just going to notice that 0 is going to equal t. Okay, that's because I plug in 0 for x, right? The x value is 0, so t equals 0. And when I plug in 0 for x, I get, or for y, I get y equals, and you can see that it's going to be just 0 plus 0 squared plus 2 times 0, and so that's just 0. So we're going to have t is going to be greater than or equal to 0, and then the other value, okay, we're going to go to 1, and so t will end up equaling 1. All right, because there's the t equals 1, x equals 1, so t equals 1. And then if I plug in y of 1, that's going to equal 1 squared plus 2 times 1, which equals 3. So t is going to be defined from 0 to 1. So my complete parametrization on this interval would be x of t equals t squared plus 2t, and then my interval goes from t greater than or equal to 0 to less than or equal to 1. Now 2. What about the second one that we have? So we got x of t equals t minus 2. So what I'll do is I'll let 0, right, my value for x, equal t minus 2. So that gives me that t equals 2 is the lower bound on my interval. Okay? Now y of t, or excuse me, for 1, we're now getting 1 equals t minus 2. And so that means that t equals 3. So this particular parametrization for x of t equals t minus 2 and y of t equals t squared minus 2 is going to end up being, okay, t squared minus 2t, excuse me, is going to end up being t is going to be greater than or equal to 2 and less than or equal to 3. So what you can see here is by changing that parametrization for x, that we get actually a different interval on which our parametrization is defined. Basically what's going to happen is that we're going to get kind of a different path. The function will travel along a different path. Okay? So basically what we're doing in this case is we're going in, we're substituting in, all right? We're going to pick a parameter for x, and we'll substitute back into y and then simplify. Okay? And we're going to basically do the same thing when we go out and find the bounds in terms of t. The last portion of this video that I want to talk about is about parametrizing conic sections and circular objects. Objects that actually are probably going to be best parametrized using cosine and sine. So what we're going to do, let's take a look and we'll consider this ellipse. All right, so we've got an ellipse, and we can see we've got the plus sign in between the two squared terms of x and y, and it's set equal to 1. So what we know is that cosine squared t plus sine squared t is going to end up equaling 1. So what I'm going to do is I'm going to use that fact and the fact that this is written in this form in order to actually translate my equation into a parametrization and a valuable parametrization. So I'm going to let x minus 1 squared over 4 equal cosine squared t. And I'm going to let y minus 2 squared over 9 equal sine squared t. Okay? And then all I'm going to do is then solve for x and solve for y. So I get x minus 1 squared equals 4 cosine squared t. And then I get x minus 1 equals now 2 cosine t. Okay? And we'll just consider the positive sides. Okay? And so x is going to equal 2 cosine t plus 1. And so that's the parametrization for x. For y, what we're going to do is now we're going to say, okay, so y minus 2 squared equals 9 sine squared t. So y minus 2 is going to equal 3 sine t. And so y is going to equal 3 sine t plus 2. What you'll notice is, and as you get better and better at these things, you'll start to notice how it is that you can look at a parametrization like this particular one and see an ellipse, right? The fact that 3 and 2, these two values, in fact, are not the same, all right? That they are not actually this, like in the case of the circle, it's not 4 sine t and 4 cosine t, or 2 cosine t and 2 sine t. And also that we're adding a particular number to it. And this particular number happens to be the value for the center of this particular ellipse. So this is the center, and it actually gives us our eccentricity as well. So in many ways, this might actually be easier to read, right, than our standard form, than the rectangular form for the ellipse. So whenever you're going through and parametrizing conic sections or circular objects, we want to remember our Pythagorean identity, right? It's going to end up making things a lot easier for us. So this finishes our fundamentals of parametrization video. One of the things that I want to point out, or I want to make sure that is very clear here, is that I've gone through and I've kind of like demonstrated a bunch of different techniques for eliminating parameters, finding parameters, even graphing some parametric curves. But what you really want to get here, like the big idea here is there's a big reason for parametrization. And it is essentially for us to be able to imagine math in terms of some other value, right? Some other kind of like hidden value or added value, for example, like a t or something along those lines. So what we can do is we can transform mathematical equations into parametrizations, okay, or mathematical functions into parametrizations that then allow us to talk about the paths of objects, right? So it adds this wrinkle, this beautiful wrinkle that you're going to get into as you get into multivariable calculus, where what we do is we now, instead of just talking about, this very kind of cut and dry, as x goes up, y goes up, or as x goes down, y goes down, or things along those lines, we get this whole idea of movement through space, right? Movement of an object through space. So that finishes the lecture. These give you just some of the basics, and good luck on the homework.